Here's a claim that should sound insane. You can inject your own code into the running Linux kernel on a production server under real traffic, and the kernel guarantees it cannot crash. Not probably won't crash, cannot. This isn't a research prototype. It's how Netflix engineers watch every disk request on a live box. It's how Cloudflare drops attack traffic before the kernel even allocates memory for it. It's how packets get routed between containers on Google's cloud. And the reason it should sound insane is simple. Kernel code runs with total privilege. There's no safety net down there. One bad pointer in kernel mode doesn't kill a process, it can take down the entire machine. So how do you hand the kernel a program it has never seen and run it safely? The answer is a tiny virtual machine, a mathematical proof, and a compiler, all hiding inside the kernel. This is how eBPF actually works. Your programs live in userspace, inside a quarantine the hardware enforces. If one crashes, the operating system shrugs and moves on. The kernel is different. It sees everything, every packet, every system call, every disk request, which makes it exactly where you want your monitoring, your firewall, your profiler to live. But before eBPF, you had 3 options and they were all bad. Option 1, change the kernel itself. Write a patch, convince the maintainers it belongs upstream, wait for distributions to ship it. That's years for a feature that has to make sense for everyone. Option 2, a kernel module. Loads instantly, runs unrestricted, and that's the problem. A single null pointer dereference doesn't kill your module, it can panic the whole machine. Option 3, stay in userspace and copy data out. Slow and blind to most of what the kernel does. What you actually want is to run your logic, at the kernel's events, with the kernel's data, without the ability to break anything. The funny thing is, a tiny version of that machinery had been sitting in the kernel since the 90s. 1993, Steve McCann and Van Jacobson published the BSD Packet Filter, BPF. The problem it solved? tcpdump. Capturing packets meant copying every single one up to userspace, just so most could be thrown away by the filter. Wasteful. Their fix flipped it around, send the filter down instead. BPF was a tiny virtual machine inside the kernel. Your filter compiled to a few bytecode instructions, and the kernel ran them against each packet, so restricted it was safe by construction. For 20 years, that's all it did. Filter packets. Then, in 2014, Alexei Starovoytov rebuilt it into something general. Extended BPF shipped in Linux kernel 3.18. The VM grew up, 10 general-purpose 64-bit registers plus a read-only frame pointer, a 512-byte stack, key-value maps for state, helper functions to talk to the kernel, and a dedicated system call, BPF, to load it all. Crucially, the new instruction set was designed to map almost one-to-one onto real CPUs. This thing was built to be compiled, not interpreted. The packet filter had become a general-purpose computer with the same safety obsession. So what actually happens when you deploy an eBPF program? Follow one through the pipeline. You write a small program, usually in a restricted subset of C. Clang compiles it, but not to x86 or ARM. It compiles to BPF bytecode, instructions for that virtual machine living inside the kernel. Then you hand the bytecode to the kernel through the BPF system call, and here's where eBPF parts ways with kernel modules. The kernel does not take your word for anything. Every program must first pass through the verifier, a static analyzer that inspects the bytecode, instruction by instruction, before it's allowed to exist in the kernel. Fail one check, and the load is rejected on the spot. Your program never executes a single instruction. Pass, and 2 things happen. The bytecode gets JIT-compiled, translated into your CPU's native instructions. Then it's attached to a hook, a specific event inside the kernel. From that moment, your code runs every time the event fires. Everything hinges on that one gate. So how do you prove a program can't crash before ever running it? The verifier's job is to prove, before your program runs, that it can never harm the kernel. It does this in 2 big moves. First, structure. It builds the control flow graph of your bytecode and walks every branch. Unreachable code? Rejected. A loop it can't prove will terminate? rejected. For years, that meant no loops at all, since kernel 5.3 bounded loops are allowed once the verifier can prove the bound. Second, simulation. The verifier steps through every reachable path, tracking the state of every register at every instruction, not just types, ranges. This register holds a packet pointer that's been bounds checked. That one holds a number between 0 and 255. Read a register you never initialized? Rejected. Dereference a pointer before checking its bounds? Rejected. Try to leak a raw kernel address out to userspace? Rejected. Exploring every path is expensive, so there's a budget. Early eBPF capped programs at 4,096 instructions. Since kernel 5.2, the verifier will analyze up to 1 million instructions before giving up. Notice what this means. The kernel doesn't police your program at runtime. It simply refuses to run anything it can't prove safe. The sandbox is a proof. Once verified, your bytecode gets one more transformation. The JIT compiler translates it into native machine instructions, real x86 or ARM, running at full kernel speed. The virtual machine was just the loading format. On modern kernels, what executes is native code. But native code that runs? When eBPF programs aren't processes, you don't call them, they attach to hooks and events call them. A kprobe can attach your program to almost any function in the kernel, dynamically, on a live machine. No reboot, no recompile. Want to know every time the kernel opens a file? Hook it. Tracepoints are the stable version, marked spots kernel developers maintain on purpose, so your tooling doesn't break between kernel versions. XDP hooks into the network driver itself, touching packets at the earliest possible moment. More on that in a minute. Other program types filter packets on sockets or attach to security hooks and veto operations. In every case, the model is the same. An event fires in the kernel. Your verified JIT-compiled program runs right there with the event's data in hand. You don't call eBPF programs, events do. There's a catch in the event-driven model. Each invocation of your program is short-lived. It runs, returns a verdict, and it's gone. Its stack disappears with it. So where does a packet counter live? Where do results go? The answer is BPF maps, key value stores that live in the kernel, created and managed through the same BPF system call. Your kernel program reads and writes them through helper calls, and userspace can read and write the very same maps. That's the bridge. Picture a counter of packets per source address. The eBPF program increments it in the kernel on every packet. Your dashboard reads the map from userspace at its leisure. No packet is ever copied up. Maps come in flavors: hash maps and arrays for lookups. Per CPU variants, where each core gets its own copy, no lock contention on hot paths. Ring buffers for streaming a live feed of events up to userspace. And the bridge runs both ways. Userspace can push configuration down, like a block list the program consults on every single packet. Programs are the verbs. Maps are the nouns. Now the flagship demo of why the hook location matters: surviving a denial of service flood. Normally, when a packet arrives, the driver hands it to the kernel, which allocates an SK buff, the heavyweight structure that tracks a packet through the network stack. Then the packet climbs: the IP layer, the firewall's rule chains, the TCP layer. If your firewall finally drops it up there, you've already paid for most of the journey. Under a flood of millions of junk packets per second, that accounting alone can saturate your CPUs. XDP, the express data path, moves the decision to the earliest possible point, inside the network driver, before the SK buff even exists. Your verified program looks at the raw packet bytes, checks a map, say, a blocklist userspace keeps updated, and returns a verdict. Drop, pass, bounce it back out, or redirect it elsewhere. The numbers are dramatic. Cloudflare's XDP-based mitigation has dropped over 8 million packets per second during real attacks, with barely a rise in CPU. Meta's Katran, the XDP load balancer open-sourced in 2018, fronts traffic for Facebook. The cheapest packet you'll ever process is the one you drop before the kernel even names it. Once you can safely run code at any kernel event, a whole ecosystem falls out. Start with observability. bpftrace gives you a one-liner language for live kernels, think awk, but for system calls. One line of bpftrace attaches a probe and builds a latency histogram on a production box, no restart, no instrumentation in your app. Brendan Gregg and the performance team at Netflix popularized whole toolkits of these. ExecSnoop prints every process the moment it launches. Biolatency histograms your disk I/O in real time. Then networking. Cilium implements Kubernetes networking, load balancing, and security policies in eBPF rather than long chains of iptables rules. And it's the engine behind Dataplane v2 in Google Kubernetes Engine. One problem haunted all of this: kernels differ. A struct's layout on one version isn't its layout on another. The fix is CoRE, compile once, run everywhere. The kernel ships type information about itself, called BTF, and programs are relocated at load time to match the running kernel's layouts. One compiled artifact, many kernels. The kernel stopped being something you work around. It became something you deploy to. To be fair, the guarantee has a price, and you should know it. eBPF programs must provably terminate, no unbounded loops ever. The stack is 512 bytes. You can't call arbitrary kernel functions, only vetted helpers, plus, more recently, specific kernel functions explicitly opened up to BPF. And the verifier is a strict, sometimes maddening gatekeeper. It rejects anything it can't prove safe, including some programs that are perfectly correct. Developers genuinely fight it. One more thing. After the Spectre era, unprivileged eBPF is disabled by default on modern distributions. In practice, loading programs is a privileged operation. But look at what that price buys. The kernel sees everything and used to be untouchable. Now, a restricted virtual machine gives your code a safe shape, a verifier proves it harmless before it runs, a JIT makes it native fast, maps give it memory and a bridge to userspace, hooks put it exactly where events happen. The idea has even escaped Linux. Microsoft maintains an eBPF runtime for Windows. The kernel stopped being a black box and became a platform. That's how you run code inside the kernel without crashing it. You don't trust the code, you prove it. Thanks for watching.